Okay, so now we're moving on to section 6 where we're going to talk a little bit about blood flow. But before we can get into the logistics of blood flow, we need to kind of define some terms. So, what is blood flow? Basically, blood flow is the volume of the blood flowing through a vessel or an organ or an entire circulation within a given period. So, we could talk about the blood flow through our kidney, we could talk about the blood flow through our aorta, or the blood flow through our entire systemic circulation or pulmonary circulation. Typically, blood flow is measured in milliliters per minute. If we think about our entire vascular system, blood flow is equivalent to cardiac output. So we already talked a little bit about cardiac output in the previous chapter, where cardiac output was equal to heart rate times stroke volume. This is the case if we're under resting conditions, and it's fairly constant. If we're talking about blood flow through a specific body organ, then it can vary depending on whatever our body needs are at the time. The other term is blood pressure. So blood pressure is actually referring to the force per unit area that's exerted on a vessel wall by the blood that it's actually holding. If we're talking about blood pressure, the measurement unit is millimeters of mercury. So if we talk about the blood pressure, say in our aorta, we could say that it's 120 millimeters of mercury. Pretty much if we're talking about blood pressure, we're talking about systemic arterial blood pressure in our largest arteries near our heart. So if you've ever had your blood pressure taken, that's what it's measuring right there. The pressure gradient provides the driving force that helps keep blood moving from higher areas to lower pressure areas throughout the body. All right, another term that we need to talk about is resistance. So resistance is basically the opposition to flow. And what resistance is measuring is the amount of friction that blood is encountering as it passes through these vessels. Most friction is actually going to be encountered in our systemic circulation, so not our pulmonary circulation, but the one where it's going to our body tissues. And where the resistance is occurring is actually really far away from the heart, and we generally use the term total peripheral resistance. We do have 3 sources of resistance, so blood viscosity, vessel length, and vessel diameter. I would definitely make sure you understand if we increase blood viscosity, what does that do to resistance? If we decrease vessel length, what does that do to resistance or the diameter, so on and so forth. The relationships are pretty important. So if we're talking about blood viscosity, we're talking about the thickness or the stickiness of the fluid. So the greater the viscosity of a fluid, the less easily those molecules can slide past each other, and the more difficult it is to get and keep the fluid moving. So think of something like sludge or like a milkshake that your textbook likes to use. So if we're talking about how thick something is or how sticky something is, blood would have a higher viscosity than, say, water. Why does it have a higher viscosity? Because blood also includes our formed elements. So our leukocytes, erythrocytes, and platelets, along with some protein. So that's going to increase the viscosity. Typically, our blood viscosity remains fairly constant. However, different conditions can affect the viscosity of our blood. So if we have too many red blood cells, that's going to increase the viscosity. On the other hand, if we don't have enough red blood cells, in the instance, say we have anemia, then our blood would be less viscous and more fluid. The other thing is blood vessel diameter. So the longer the blood vessel, the greater the resistance that's encountered. So if we're talking about the opposite would also be true. So the shorter the blood vessel, the less resistance that it would encounter. So blood viscosity and blood vessel length are relatively constant, like I mentioned before. The last one is blood vessel diameter. So the relationship between the diameter and the resistance is pretty straightforward. So if we have a smaller diameter, that's going to mean a greater resistance. If we have a larger diameter, that is a lower resistance. So a good analogy that your textbook uses is a straw. If we're trying to drink something that has a little bit of viscosity, so something like a milkshake, it's not water, would you get the most milkshake in your mouth with the shorter or wider straw or the longer and skinnier straw? You'd be able to get more through the thicker and wider straw. So the larger diameter would increase this. Why does this happen? It's because basically the fluid closest to the walls moves more slowly than that in the middle of the tube. This is called laminar flow. So laminar flow is similar to like a river. So if you've ever looked at a river and the way the water is moving, the water that's close to the bank or the edges moves much slower than that of the middle of the river because of resistance. So the wider a river, the greater the flow is going to be down the middle. So because it's further away from the edges or the resistance itself. Another thing to think about is that resistance varies inversely with the fourth power of the vessel radius. So if we increase the radius, we're going to decrease the resistance, because if we increase the radius, we've increased the diameter. If we've increased the diameter, we've lowered the resistance, and vice versa. If our radius is doubled because of the formula, the resistance is going to drop by 1/16 because it goes to the fourth power of the vessel radius. That's not super important to remember, but I will say that resistance is equal to 1 over radius to the fourth power. So smaller diameter arterioles are going to be our major determinants of peripheral resistance because they have the highest resistance. And because of that, small diameter arterioles are going to constantly change their diameter or their radius frequently to adjust the amount of flow that we want into something. If we have any abrupt changes in our diameter of whatever blood vessel we're talking about, or if we have any buildup like from fatty plaques, that could also increase resistance. So that laminar flow that we were just talking about, that's like our river, that would be disrupted, and then it's going to become turbulent flow because now we have these plaques along our blood vessels. And turbulent flow is just an irregular flow that causes increased resistance. So how do we relate all of these different terms that we just talked about? Well, a formula. And again, it's not as important that you know the formula, although you should, but rather understand the relationships that the formula represents. So blood flow is designated a capital F, and it's directly proportional to the blood pressure gradient. So blood pressure is represented as a delta P right here. And the delta symbol just means the change in pressure. If our pressure increases, then our blood flow speeds up. Blood flow is inversely proportional to the peripheral resistance. Peripheral resistance is represented by the capital letter R. If we increase our resistance, then our blood flow is going to decrease. So they're inversely proportional to each other. And that equation did not print right. So blood flow is equal to the change in pressure divided by resistance. Because pressure is on the numerator, that means it is directly proportional to flow. So if we increase flow, we increase pressure. If we decrease pressure, we decrease the flow. The opposite is true if we're talking about resistance because it's on the denominator, and that means it's inversely proportional to flow. If we increase resistance, it lowers our flow. If we decrease resistance, it's going to increase our flow. When we're talking about all the components of this formula and blood flow in general, resistance is going to be the most important in influencing local blood flow because we can easily change it. We can't really change, at least quickly, the length of our blood vessels, so we really are focusing on the diameter or the amount of resistance.